All right, we're gonna go ahead and get started. Is our face-to-face test three and our final exam start and then the same dates? Not exactly the same dates, Nestor. Let's check out what's going on here. Just make sure I didn't miss anything else. So, I can't remember the exact dates, but I put them either in an announcement or an email, so that's what I refer to, and I'll refer you to that. Uh, but the last day to complete your final exam would be by noon on March 4, or excuse me, on May 4th, which is the Monday, uh, 2, 3 weeks from now. But it has to be done by noon. So I've made the practice final exam disappear by 11 a.m. that day, and then the practice test, actually, since it's part of practicing for that final as well as for that last face-to-face test, that's going to stay available up until 11 a.m. On the 4th as well. The If I remember correctly, I think what I did was I made the last face-to-face test due until the week before or something. But anyways, I'll just refer you to my emails and my uh, announcements for that. If not, if I what I'm going to do is, since you asked me that, I'll look back through all that, and if it doesn't seem like I put that out in an email or an announcement good enough for everybody to see, then I'll just go ahead and and resend everything out. So you guys got to keep an eye on that. What I wanted to show you, I'm going to go ahead and share my screen with you and show you what I've added now. So what you'll see is in practice tests, we now have the practice tests for the last face-to-face test, which runs all the way through April 28th. But that's basically a test for online test 5 as well as for face-to-face test 3. And that was before I had well, no, that was for actually the right date. So April 28th evidently is the deadline for the face-to-face test 3 for you guys. What you also see, and this is misworded, this should be OT06, but what it is a practice test '07 for the extra credit online test 7. So I've created sort of another online test, and the reason why I say sort of is because the online test that we had was online test 5. That was supposed to be the last one, and I've now made an online test 6 that's you can take if you want. So, for instance, if you're one of the students that missed an online test before, or if you're one of the students that just got one in and maybe didn't get a perfect 100 on it, here's your opportunity to replace that with a 100. If you don't take it, it's just going to count as a 0. But I'm also dropping 2 of the lowest online test grades instead of just 1. So in that sense, it's extra credit. But in my reasoning, it's another opportunity for you to get some confidence in your chapters 10, 11, 14, and 15 before taking the final exam, which includes 10, 11, 14, and 15. So that's why I've made that one available up through May 4th, May 1st, because that's when that online test is due. And it's more geared towards those last chapters, 10, 11, 14, and 15, which only 9 and 10 are covered in the online test that's due. Additionally, you have a practice final exam that's right here, and you have to have your final exam done as a. Oh man, I just see that it's. Uh, don't mess with this one yet. Evidently, it imported with none of the questions because it says 0 points right there. That makes me mad. I made up 2 versions of it specifically so it would make. But this will be back up tonight. So it will be here. It just says PFE, that's practice final exam, chapter 1 to 11, including 14 and 15 as well, spring 26. That's going to be your practice final. That's probably what you should focus on here on out. Additionally, I'm making an announcement now. The plan that I had for you students, and I've had it since the beginning of the semester, I do it just about every semester, is that I warned you that I would give you another way of making up for bad homework grades because I realize the online homework systems have errors in them. They're not perfect. Sometimes they're a pain in the butt, that sort of thing. So I told you don't worry too much about getting hundreds. Try to do as well as you can, but if if you can get like in the 80s or something, you're probably fine. So the deal is I am going to calculate your grade without any homework grade whatsoever, and I'm going to calculate your grade with a homework grade. And if your homework grade is bringing your grade down, I'm going to toss that and give you the other grade. And that's done automatically. You don't have to ask me to do it. I just take the calculation according to the syllabus. I calculate exactly what your grade should be. Then I take those same relative percentages for each of the parts of our course, which would be, online tests. Of course, I'm leaving out the homework, but online tests, face-to-face tests, that will all be left alone, and everything else will be basically the same. The online test versus the final exam versus the face-to-face test, those relative percentages will be the same, but it will not include the homework. So I will even have in your grade book separate columns. One column will say grade without homework, and the other one will be the regular syllabus grade. So don't worry about your homework score dragging you down. If it drags you down, it's not going to be an issue. What you need to focus on is obviously if the homework is helping you learn, then by all means do the homeworks for chapter 11, 14, and 15. If you're having problems and you're just wanting to prepare for the test, then don't even bother with the homework because I'm going to throw that homework grade out if you don't like your grade. And you can just start focusing on the practice tests, which include all the material that I'll test you on. So, anyways, that's all here. I again refer you to my emails and announcements. I put that stuff in writing specifically so I don't have to memorize and remember the results and don't have to screw it up. So, I very rarely will state something verbally unless I have the object right in front of me, and I don't right now. So, that's what's going to go on with that. Anybody have any questions before I move along?
Oh, yes, Prof. I had a quick question.
Yes.
Are we taking the final by the fourth, or is that practice test just there by the fourth?
No, you have until noon to finish the final exam on the 4th. In other
Okay,
words,
so
if
that
if you can schedule a appointment at a testing center or whatever by the 4th, as long as you're done by noon, then I'll count it. But if you're not done by noon, then you're going to get a zero and you'll fail. So just make sure you get it done by noon.
gotcha. So the final exam can be taken like on May 1st,
Yeah.
right? Okay,
Yeah, you can
cool.
take it on any day. Actually, I'm going to make it available. I believe the last week of school is the week before the 4th. The 4th is a Monday, so it'll be available all that week to take it as well as the Monday thereafter.
Perfect.
That makes sense? All
Yeah,
right.
yeah.
Anybody else have any questions? Okay, and remember there will be an extra online test, but again, you're not required to take it at all. It's just one of those things where it can't hurt your grade at all because if you decide to take it and get the highest grade of 12 on it, I'm dropping the lowest two online test grades. So unless you happen to have a grade, uh, well, no, even then, it's always going to help you, or your grade will stay exactly the same. So it's there. Plus, it's more focused, and then you also have the online quizzes for individual chapters. So if you look above practice tests, there's chapter practice. And for instance, right now, you guys might want to focus on chapters 14 and 15, maybe 11 to a lesser extent, but 14 and 15 are the ones we're covering today and next time. So maybe that might be a good choice for you. With that being said, I'm going to go ahead now and share my iPad screen. Anybody have any last minute questions before I move on? Okay. So when we last spoke, we were in chapter 11, and the last example I did was chapter 11.7, example 11.7. So that was the last one I did. That's pretty much pretty close to the last of the types of problems between me pointing them out to you and then me giving you actually examples. I've covered all the major material. That being said, I still would like to show you another problem or two. So what I've decided to do is I'm going to do an example 11-11 from your textbook. And then I'm going to do another example 11, I believe it's 11-12, just to for concreteness. So let's go ahead and type this out or write this out. This is example 11.11. And if you read that example, it specifically says Kepler's second law derived. Kepler's second law states that each planet moves to so that a line from the sun to the planet sweeps out equal areas in equal times. Use conservation of angular momentum to show this. So that's what we're wanting to do. So what I'm going to do is I'm going to draw an ellipse approximately. Oh, that's a horrible ellipse. But let's see if I can draw it a little better. There you go. So that's roughly an ellipse, and it's kind of a pain because I really want it to tilt it a little bit, but I've got it tilted by mistake. What you'd imagine is this would be our sun. And for instance, if you had a particular planet in mind, then at one point in time, the planet would be there, and that vector would be the r vector. In other words, we're pretending like the vector or the coordinate origin is at the center of our sun. So a vector from the center of our sun to the location of the planet would be the r position vector. Now, if we consider that a short time later, then that r position vector would have moved to roughly here, and that distance traveled along here would be technically, let's see if I can draw it like this. This distance right here would be v times dt. In other words, if you take the velocity that it has, now we're dicing this up very narrow, so that angle that I'm showing is actually markedly larger than it should be. This should be an infinitesimal angle. And that small angle would suggest that it's so small that it's very reasonable to assume that the velocity of the planet's not going to change any over that little interval. So the distance traveled there is v dt. Now, the actual velocity, since it's possibly an ellipse, which a special case of an ellipse is a circle, and if it were a circle, then the velocity vector would be perpendicular to the position vector at all times. But this one's not the case because this is an actual ellipse, and the velocity vector will actually have some angle other than 90 degrees for most of the time. So this is the angle, or this is the vector that's the velocity. And if, for instance, we considered these two vectors r and v tail to tail, then this vector right here, or excuse me, this angle right here would be the angle theta. In other words, the angle theta that we're used to from cross products and things like that. In other words, two vectors, when they're tail to tail, are separated by an angle theta. And if you're taking the dot product of those two vectors, then the dot product is the magnitude of the first times the magnitude of the second times the cosine of that angle theta. If you're taking a cross product, the magnitude of the cross product is the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them. That's what that angle is. Now, because of that, and I'm going to draw it a little smaller here and put it at a slightly different place. Because of that, what we can see is there is an idea of having a vector that makes a right triangle with the r, and then this is the angle theta. And now, with that in mind, you can see that the triangle swept out. If, of course, I'd move that green arrow or that green line to over here, so it'd be in that spot. Actually, let me go ahead and do that because it's going to look confusing otherwise. So I'm going to zoom into that area a little bit, and what we're going to imagine again is this is our velocity vector, and this is our r vector continued on. Now, what we're going to do is say that we could make a triangle out of this velocity vector. Let me make this velocity vector just a tad shorter just to make it, well, for a very specific reason. But, oops, wrong vector here, color. Okay, so this is our velocity vector right there. Now, you can treat this velocity vector v as if it has a component that is perpendicular to the r, which would be that one, and parallel to the R, which would be that one. But the important thing here is that distance is approximately the base of a triangle. So when we're looking at this, we can say that this angle right here is theta. And of course, that also gives you this angle in there. That angle is also theta, so that you see this side is, you can look at it as v dt sine theta. Now, the whole reason we're doing that is because if I know for an infinitesimal slice like we've done here, if I know that shape is a triangle, then I know the area of that triangle. So I'm going to say the area of that triangle, dA, is 1/2 base times height. Well, I'm going to argue that the height is r and that the base is, in fact, v dt sine theta. So, with that in mind, we have, going back to blue, dA over dt would be 1/2 v dt r sine theta over dt, which equals, what I can do now is say, the DTs have canceled out. So you can see this DT cancels out with that DT. And we can see, for instance, that I have a 1/2 and then I have a VR sine theta. Well, this is where the important thing comes in. The important thing is that the angular momentum L is equal to R cross P. So R vector crossed with the P vector, which is R vector crossed with MV vector. So what we see is the magnitude of L, as I was just mentioning to you before, would just be R times M times V times the sine of theta. So what we can see is V times R times the sine of theta is really close to the angular momentum. If I multiplied top and bottom by M like that, then what I would have is dA over dt, the differential area change over time, is equal to 1 over 2m times m. Let's write it a different way. I'm going to write it in an order that might be a little bit more constructive or visually helpful. So r times m times v times sine of theta, like that, is what we have left. Now you can see that dAdt is in fact 1 over 2m times the angular momentum. So the instantaneous rate of change of the area, the dAdt, is in fact equal to a constant, and that's what we set out to prove. Specifically, it says use conservation of angular momentum to show that uh, Kepler's second law states that each planet moves so that a line from the sun to the planet sweeps out equal areas in equal times. So equal area and equal time can be basically stressed by the fact that dA over dt is a constant, and you see that it's clearly a constant. Any questions on that? All right, so that one's just one that I thought would be instructive to see, but it also allows us to tie back to our understanding of, for instance, chapter 6 in Kepler's laws. Now I'm going to go to example 11:12, and this is really the last example from chapter 11 that I'm going to cover. And this example, it says, bullet strikes cylinder edge. A bullet of mass m, lowercase m, with a velocity, lowercase v, strikes and becomes embedded at the edge of a cylinder of mass capital M and radius capital R with the subscript 0, as shown in figure 1122. The cylinder, initially at rest, begins to rotate about its symmetry axis, which remains fixed in position. Assuming no frictional torque, what is the angular velocity of the cylinder after this collision? Is kinetic energy conserved? So that's the big question. Now, let me show you how we're going to work this out. I'm going to start off drawing a circle. So there's a circle. And now I'm going to draw some distance away is a little bullet. So here's my little bullet. And my little bullet has a mass, lowercase m, and the velocity that I'll use the Greek letter nu for because it looks like a V. And it's a little different, so we can use it to look different. But what we've got going on here is this bullet is aimed just to the edge of that circle or that cylinder. And that cylinder has a radius r0 and has a mass m. Now, in this case, what's going to happen is we can treat the system to be the bullet lowercase m with velocity nu and the cylinder capital M and radius r0 not moving at all. We can treat that as the system. If we chose to treat one of those as a system without the other, then we'd have a problem because clearly the cylinder is going to put a great force on the bullet, and clearly the bullet is going to put a great force on the cylinder, both of which are going to result in torques. And torques are what makes us not have conservation of angular momentum. So, in order to have conservation of angular momentum, we're going to treat the system as little m and big M together. Now, this is sort of a trick question, so I tell you that because I expect you to get it wrong. If you don't, that's great. But if you do, that's not a problem at all because most people would agree with this. But would anybody think that this system has any angular momentum right now? So they haven't collided yet. I just got a bullet flying towards it like that, but it hasn't touched anything. Is the angular momentum different than zero right now? Anyone? And I put the chat window up in case anybody typed it in. Give you a second to answer that. Okay. No one shows an answer, so the typical answer is no. There's clearly no angular momentum because nothing's rotating around anything else. But remember, the angular momentum is given by L is equal to R cross P. So unless the velocity of this particle happens to be parallel to the R vector, which in this case we're going to use as the vector that points from the center of the cylinder to the bullet mass m. If those two were parallel or anti-parallel, then the angular momentum would be zero. But because they're not parallel, then we're going to have an angular momentum initial given as follows. So here's the initial angular momentum. It's just the magnitude of r cross p. And the magnitude of r cross p is going to be uh, a vector that we might draw from here to, oh, I should probably do a different color. I'm going to do a vector from here to here. That is the vector r. And now if I calculate r cross p, I'm going to say r cross m v like that. And of course, since I did it as a cross product, that makes this a vector. But that means the magnitude of it, L sub I, is equal to the component of the R that is perpendicular to the MV. Remember when we learned about torque, it was torque equals R cross F. But I said you could also write it as R times F times the sine of theta. And then I showed you that r times the sine of theta is the component of r perpendicular to f. And then I showed you then I showed you f times the sine of theta is the component of f perpendicular to r. So just like that, we can also say that the magnitude of L is equal to r times f, r times mv times the sine of the angle between them, or it can be r perpendicular times mv, or it can be r times mv perpendicular. So because of that, the component of r that's perpendicular to v is r0. So we're going to get r0 times m times v. That's our initial angular momentum. So it's perfectly fine if you thought the initial angular momentum was zero. I would have thought it too when I first took this. I actually did think this when I first took a equivalent course. That was actually an algebra-based physics when I first ran into it. So by the time I got to calculus-based physics, I already knew the right answer. But it was perfectly natural seeming to me that there was no angular momentum there. But because that v happens to be not aimed directly at the center of rotation of this object, that gives it a component of r that's never going to be zero. Therefore, I can do that. So that's what the initial angular momentum is. Now, after the fact, the angular momentum will be L final is going to be I times omega, because now it's just a singular object that has a moment of inertia I, and it's going to be rotating about an axis with an angular speed omega. In this case, the I is going to be the I for the cylinder, which is 1/2 m capital R zero squared, plus the moment of inertia for a point particle orbiting about a radius r0 from the center of an object. So in this case, it's going to be plus m r0 squared, and that's our omega final. I'll go ahead and subscript that final so it won't confuse us. Now I can set L initial equal to L final, because conservation of angular momentum is a fact because the sum of the torques acting on that system is zero. So now I can say R0 times M times V is equal to 1/2 M plus M times R0 squared times omega F. You can see right now that the R0, one of them is going to cancel out. And now I get that omega F is in fact equal to M times nu divided by M plus 1/2 big M times R0. And that is the actual angular velocity after they stick together. Anybody have any questions on that? Now, you can go ahead and you probably already know it, but it specifically asked you, was kinetic energy conserved? You know that, at least in linear momentum, when we had two objects collide and stick together, that was called a perfectly inelastic collision. So you would probably guess that this does not have conservation of kinetic energy. And the way you can go about seeing that is you can go ahead and say K initial is just 1/2 lowercase m v squared. K final, on the other hand, nothing is moving, nothing's translating. It's all rotating about a center. So all I have is the 1/2 I omega squared. So in this case, it's 1/2 I. And remember, the I was, I'll start it with the lowercase m since I did that the last time. It's m r0 squared plus 1/2 capital M r0 squared times omega final squared. So K final minus K initial would be the actual change in angular momentum. So I could actually go ahead and do this calculation, and it would be 1/2 times M R0 squared plus 1/2 M. Actually, let me go ahead and factor out that R0, because uh, might as well. It's going to be something nasty otherwise. So I'm going to say this is 1/2 times M plus 1/2 times big M times R0 squared times omega final squared. Now that's going to be M squared nu squared over M plus 1/2 M squared times R0 squared. Now you can see that this R0 squared is going to cancel out. Oops, why'd that go away? Uh, there you go. It just, I assume y'all aren't seeing my iPad right now. Now you're seeing it again, hopefully. Okay, so squaring all this allowed me to get rid of the R0 squared. It also allows me to get rid of one of these, which I'll mark out with an X like this. So that's what happened. And it turns out now that I've got M squared, nu squared over 2 times M plus 1 half big M. And I think that's about it. Let's see. We could do that. Let's see. M squared, V squared. Yep, that's all that. And the main thing here is you could probably do some more algebraic manipulations and stuff of that sort. Oh, I remember. Completely forgot to subtract the other part, which would be minus 1 half M V squared. So minus 1 half M V squared. So that's what the expression is. It's pretty obvious to me already at that point that this is not zero. If I wanted to be certain of that, then what I'd have to do is multiply this by 2 over 2 times m plus 1 half m under 2 times m plus 1 half big M, like that. That would get me a common denominator. And now I'd get m squared nu squared, and now by multiplying all this through by that new denominator, the 1 half times the 2 is going to give me 1, but I'll have minus m v squared times m plus 1 half big M. And then all of this has a denominator that's equal to 2 times m plus 1 half M. I can simplify a little bit more. M squared nu squared minus M squared nu squared. Notice the M, once it hits the M inside, gives me M squared. And then the minus has to be distributed too. So that's going to be a minus 1 half M big M nu squared. All that divided by 2 times M plus 1 half big M. M squared nu squared minus M squared nu squared. That's going to give me nothing. So I can now, in other words, what I'm saying is this term is going to cancel out with that term. And now I can get a negative m m nu squared over, now instead of having 2 on the bottom, I actually have 4 on the bottom. There's supposed to be parentheses there because that 1 half in the negative 1 half mv squared makes it 2. So this is going to be 4m plus 2 big M. And you see there is no common factors of M or big M that we can cancel out. So it's pretty much just going to be that. So we get negative mv squared over 2m plus 4m is the change in kinetic energy. And that is not equal to zero. So it's clearly not elastic. Any questions on that? Okay. The remaining parts of chapter 11 were a spinning top, which talks about a gyroscope, and uh, that sort of tilting and wobbling that it does is called precession, precession. And we know the Earth, for instance, does that. And the reason the Earth does it is because the Earth's equator has a slightly larger radius than it does at the poles. And because of that, that means there's a little bit bigger chunk of mass around the equator than there is around anywhere else. So when the sun is pulling on the Earth, it's pulling at the center of mass, but because it's a little bulbous around the middle, not like your instructor, it's tending to try to grab that bulbous portion of the equator and pull it upright when it's leaning away from it like that. But just as quick as it's trying to pull upright, the Earth is rotating this way so that it tends to do this wobble thing instead. Well, you can use the laws of physics and calculate what that wobble is. And if I remember correctly, it's been a while since I've done this calculation, but if I remember correctly, it's on the order of 22,000 years is the period of oscillation for precession. It might even be 40,000 years. So that is something that actually happens, but it goes so slowly we don't notice it over human lifespans. Uh, I'm not going to require you to know any of that. I'm not going to require you to solve any of the physics problems associated with it, even though they do give you the precession frequency, capital Omega is equal to mg over I omega. So I'm not going to make you do that anyways. The same thing with the next section, which is rotating frames of reference, inertial forces, inertial and non-inertial reference frames, and fictitious or inertial forces, one of which is the Coriolis force. And it's it's real, meaning we can use the idea of the Coriolis force to understand why hurricanes spiral inward and that sort of stuff. But what's fictitious about it is it's not a separate force; it's more a ramification of the fact that the Earth is rotating. What I learned, like in physical geology, for instance, was a nice little trope that works well, is that the Coriolis force deflects everything to the right in the northern hemisphere and to the south in the southern hemisphere. So if you imagine the Earth as a sphere like this, then here's the equator. And let's imagine, for instance, this is the United States. There's Texas, there's Florida right there, there's North Carolina area, and there's Martha's Vineyard, the Great Lakes, stuff like that, Hudson Bay, so on and so forth. Here's Mexico coming down here, the Yucatan Peninsula, uh, South America, that sort of thing. Now, what do we mean by that? Well, for instance, if you happen to be trying to fly, let's say you want to fly from somewhere like Raleigh, North Carolina, or Richmond, Virginia, straight down to somewhere in Florida. And this actually happened. There was a really bad, tragic case of a professional golfer and his family. I mean, like his kids and his wife and some friends were all on a private jet, and they were flying somewhere from like New York towards Florida or something like that. Well, evidently the jet lost air pressure, cabin pressure, shortly after flight, and air traffic control. This was shortly after 9/11, so air traffic control tried to contact them and couldn't get a hold of them. So we scrambled jets up there to see if this was possibly a terrorist attack where someone's going to, ram this plane into something. But the pilots flew up and were able to see inside, and they could see that literally all the pilots and all the passengers had completely, more or less, passed out. And though they weren't dead, probably they were at least passed out and without any pain. And there really wasn't anything we could do. So they just had to follow it and make sure it didn't land into a populated area. Well, the Coriolis force kicked in, and what that means is something headed in the northern hemisphere is always going to veer to the right. So lo and behold, it started to drift to the right like that, and it ended up crashing like near Texas or something crazy like that, which is really a really good example of seeing how the Coriolis effect works. You can see from this perspective too that if the plane actually took off and was going south, the Earth is rotating under it like that, and that's why the plane ended up in that area near Texas or whatever. I think it might have been even Oklahoma, and they probably didn't fly from Raleigh or Richmond. I think they were flying from like Martha's Vineyard or somewhere in Massachusetts or something. But the main thing is you see that the Earth would rotate under it that way, which would make the plane seem or appear to have drifted towards the west. And it didn't really drift to the west. It just went straight down while the Earth rotated under it. So that's what we mean when we say it's a fictitious force. It's not something that goes on the left-hand side of Newton's law, which says the summation of forces equals mass times acceleration. It's something that belongs on the right-hand side because it's part of the acceleration. So, if you want to think about, for instance, a hurricane, then storms start off as low pressure, And if you had studied chapter 13, which we're not doing because that's normally covered in fluid mechanics, what you'd learn is that just like a high voltage to a low voltage causes current to run from the high voltage to the low voltage, a high pressure versus low pressure causes air or wind to fly from low pressure to high pressure. So, because of that, what we get is wind all traveling right towards the center of a low pressure zone like this. That's the way that air tends to flow around a low pressure zone. Everything comes inside. But if you think for a second, wait a second, this low pressure zone is in the northern hemisphere, therefore we realize that it's going to drift to the right. That one's going to go that way, that one's going to go this way, that one's going to go this way. This is going to go this way. I'm not trying to show it going uh, radially outward. It's just my curve of my arrows are sometimes looking that way. But the net result is that you get a spiraling of the winds so that the hurricane looks like this. And that's why by the Coriolis force, there's actually another force that you have to take into account, and it's basically the friction forces. But at the end of the day, that is actually what causes the hurricanes to spiral is this fictitious Coriolis force, which we know again, not really a force. It's just part of the acceleration from dealing with a non-inertial reference frame. Again, I'm not requiring you to do any calculations from this section or anything. I just think you should make sure you read it so you'd be an educated person who knows things. It's really embarrassing to think that if you graduate from college and you don't know, some of the fundamental facts like why does the earth precess, why do hurricanes spiral in circles, why do they circle this way as opposed to that way? All that stuff is the stuff that educated people are supposed to know. So at least take it as that opportunity to read that. But I'm not going to test you on any of that. Now that we've done that, I'm going to go ahead and move to chapter 14. Does anybody have any questions? So this is chapter 14, and chapter 14 is called Oscillations. Notice I'm not saying that as a hard C. It's almost like a continuance of the S. That's the word oscillations. I know that there's people in this world that are, perfectly functional humans that don't know that word and haven't heard of it, but I'm giving you this opportunity to learn it and hear it how it's properly pronounced. It's oscillation, not oscillation. Okay. And it's basically, you guys have learned about the sine function and the cosine function, and they do this. Anything that repeats itself like that is oscillating in some sense. So you've probably seen fans that people have in their room, and it does this and then comes back this way and blows and then this way, or sprinklers. Those are oscillating sprinklers. And you can call it oscillating even when it goes back and forth, when really we normally mean oscillation to go around sort of like orbiting a planet, but anything that repeats itself is acceptable. So, in order to make sense of this, we need to first talk about simple harmonic motion, and that requires us to recall Hooke's law. And Hooke's law says that when you apply a force F, you compress an object a distance x, and that distance is directly proportional to the force, but the force is actually in the opposite direction. So, for instance, if you are pushing, let's imagine that this bottom hand is just a table or the ground, something not actively applying a force, but just not moving. If I now push down, let's call that downward direction the positive x direction. If I push downward, then that's going to tend to compress this pencil. And according to Hooke's law, this pencil will actually get shorter by an amount x, and that x will be in the positive x direction. But this negative is telling you that, in fact, the pencil is going to push in the negative x direction, even though it's compressing by an amount x. So that's why the negative's there. It's a restorative force. So if you do something to make it move to the right, the force is going to pull it back to the left. If you do something to make it move to the left, the force is going to push it back to the right. That is the nature of something near equilibrium. So, for instance, if you had a ball right here inside of a let's say a gutter that's shaped like a U or a parabola like that, if I gave this ball a little push to the right, it would go up that way, but the shape of the gutter would force it to come right back. So that gutter is supplying what we call a restorative force. So it's acting like F equals negative kx. Similarly, if you gave it a push to the left, that gutter would cause it to go back to the right. This is called stable equilibrium. Okay. If, however, you had a setup like this, then that would be an unstable equilibrium because if you give it a little push to the right, it's going to take off to the right. If you give it a little push to the left, it's going to take off to the left. So that one doesn't have the restorative ability, and it doesn't have any way, of course, of pushing in the opposite direction. So the very first question they ask you is in example 14.1. They say, oh, nope, example 14.2, the very second question they ask you says, is the motion simple harmonic? So let's look at this. Example 14.2, is the motion simple harmonic? It says, which of the following forces would cause an object to move in simple harmonic motion? Which results in simple harmonic motion. That's an S there. Apologize for writing so rough. But the forces are A, F is equal to negative 0.5 x squared. B, uh, actually, I should say B dot is F is equal to negative 2.3 y. C is going to be F is equal to 8.6x, and D is going to be F is equal to negative 4 times theta. So it asks which of the following forces would cause an object to move in simple harmonic motion. So as I showed you, simple harmonic motion should be a result of some kind of restorative force. If you push it out to one way, it should come back the other way. If you push it to the left, for instance, the force should respond by pushing to the right, that sort of thing. So let's start off with part A. F equals negative 0.5 x squared. If if we imagine the equilibrium is at x equals 0, when I push to the right, which is the positive x direction, which way is the force going to act? Anyone? So if I push to the right, then the x is going to be a positive x, and you're going to square it, that'll still be positive, but then you're going to multiply it by negative zero point 0.5, and that's the force that it applies to that object. Well, that object's causing it when you push it to the right to move it back to the left. So that seems restorative. But what happens when we push it to the left? So if I actually move it to x being a negative number, does the force now push to the positive direction? Anyone? So
I
because the x, go ahead, Christopher.
was gonna say it should it, I think because you're switching the signs, or does it
Yeah,
continue?
you would think it would because it switches the signs, but the problem is the x squared. So when I put in a negative x in x squared, that square completely takes care of the negative. So even when you push it in the negative x direction, it's going to continue to force itself to the negative x. So it's going to run away and further exacerbate the problem, in other words. So we know that that one can't be simple harmonic motion or simple harmonic oscillations. So does everybody see why? F equals kx wouldn't work either, but F equals negative kx works because if you put in a negative x, you get F being positive, and if you put in a positive x, you get F being negative. You always need it to fight in the opposite direction. When I put in a positive x, it does fight in the negative direction, which is good, so it's somewhat restorative. But when I put in a negative x, I square that, that becomes positive x squared times a negative number. And then that means that even though I pushed it to the left, it's also applying a force to the left. So it's going to run away. So that's why that one's not good. The B is negative 2.3y. So it has the negative and it doesn't have a square. So the only problem is it okay to have a Y being vertical? Yeah, it's absolutely fine. In fact, if you hang a spring vertically, it's more natural for you to call that direction Y instead of X. And the fact that when you put in a positive Y value, you get a force in the negative Y direction. And when you put in a negative Y value, you get a force in the positive X direction. So this one is simple harmonic oscillations or simple harmonic motion. The 8.6x would work, but the problem is it's actually in the wrong direction. So we can't use that one because if I put in a positive x, it's going to continue to push it to the positive x. If I put in a negative x, it's going to continue to push in the negative x direction. So that one can't be SHO either. But the F equals negative 4 theta is also okay because it does have the negative, and in case we're talking here is sort of like a what we call a torsion pendulum. So you could imagine like tinsel, like you hang on a Christmas tree. It's that flat ribbon of metal. If you hang something from that, like this pencil, it'll hang perfectly still as long as there's no twist in the tinsel. But if you give the tinsel a little twist like this, it's going to tend to pull it back like this. That F equals negative 4 theta is just like F equals negative kx. So it's acting as a restorative force. So this one's fine. And it is a simple harmonic uh, motion force. So that's something to understand. Now I'm going to go back to example 14.1. So example 14.1 says the following. When a family of four with a total mass of 200 kilograms step into their 1,200 kilogram car, the car's springs compress 3 centimeters. What is the spring constant of the car's springs, assuming they act as a single spring? And then B, how far will the car lower if loaded with 300 kilograms rather than 200 kilograms? So what we have is a little mass equal to 200 kilograms, and I put the dot and then the zero with the underline on it so we could claim the first 3 digits as being significant. The big mass is going to be 1,200 kilograms, and what we know is X for the 200 is going to be 3 centimeters, so I'm going to write 3.00 centimeters. And the way we go about solving this is A, they wanted to know specifically what is K, so K is equal to question mark. And then part B, they want to know X 300 equals question mark because that's the case where they're saying, hey, what if we get rid of one of the people and bring your, big fat father-in-law or something? Okay, so he's going to add another 220 pounds roughly because he's, 100 kilograms. So that's the scenario. Now, what we know is F is equal to negative kx. Now, if you're ever going to take Hooke's law and plug it into some other equation, you need to include the negative. But if you're just solving for magnitudes, throw the negative away and just calculate it. Okay. In this case, what we're going to do is we have to realize what force is associated with the 200 kilograms of people. The 200 kilograms of people near the Earth's surface are going to cause a force m times g. So what we have is 200 kilograms times 9.80 meters per second, is equal to K times 3.00 times 10 to the negative 2. Notice I did have to convert that to meters, and that gives me K is equal to 200 times 9.8 gives me 1960 newtons divided by 3.00 times 10 to the negative 2 meters, and that gives me 6.533 times 10 to the fourth newtons per meter is equal to K. So that's our spring constant. Now, part B, you can be smart about it and just quickly say, oh, clearly the answer is going to be 4.5 centimeters because basically we know the force is proportional to the stretch. And if we increase the force by a factor of 150%, then we're going to increase the stretch by a factor of 150%. 150% of 3 centimeters is 4.5 centimeters. Now, if you're not quick enough to notice that, that's fine. You just have to do the work. And in this case, the work is going to be 300.0 kilograms times 9.80 meters per second is equal to K. This time we're going to assume we have the same K that we just found, which is obviously the way springs are supposed to work until you spring them. No pun intended. And then that's times x 300. So when I solve for x 300, I get 300 times 9.8 gives me 2940. But then I've got to divide that by 6.533 times 10 to the fourth newtons per meter. And the top, by the way, is just newtons. So I ultimately get just meters. And 2940 divided by 6.533 times 10 to the 4 gives me 0.04500 meters, which you can see is 4.50 centimeters. So that's how that works. Anybody have any questions on that? So this is sort of rudimentary stuff, just reminding you about Hooke's law and how that's applied. That's a very typical problem. We'll give you some data that allows you to determine K, and then we'll assume now that you know K, we'll ask you special questions as if you do know K. Some questions like, well, how much will it stretch when I add this much force? Or how much will it stretch when I add this much force? That sort of thing. So that's a very normal scenario. But we're going to have other stuff to do as well, as you'll see in these examples. So for starters, let's look at example 14.3. And it says determine the period and frequency of the car in example 14.1a after hitting a bump. Assume the shock absorbers are poor, so the car really oscillates up and down in an Uncle Buck like fashion. Highly recommend you guys watching the movie Uncle Buck. But we're going to go back to that. This is example 14.2. But before we do that, I want to remind you Newton's second law says the summation of the forces is equal to m times a. Now, we use that a lot in chapters 1 through 7 and stuff like that, but most of those times we were solving for a because it was a constant. But in general, a doesn't have to be a constant, and then this F equals ma becomes a differential equation. In other words, the summation of the forces is equal to m times d2r over dt squared, where r is the position vector as a function of time. You could use x of t or y of t or z of t, but generally we try to use r so that no one thinks automatically if I used x of t that it must be in one dimension and acting left and right. Using r sort of takes that away. But that's what Newton's second law is. So if we apply Newton's second law to a one-dimensional spring, what we get is the following. F equals negative kx, and that's the only force acting, so I'm going to write negative kx is equal to the mass on the spring times d2x over dt squared. Now, that's not fun to write, and in fact, it turns out that there's a lot easier way, and it's Newton's differential methods, in other words, differential notation. And if we want to do that, then we can write this as negative kx is equal to m times x double dot. So if you put a dot over a x function, that means a derivative with respect to time. Similarly, when you put a prime mark next to x, that means the derivative, or the prime next to an f, for instance, that means the derivative of f with respect to x. So the primes usually mean with respect to space, and the dots mean with respect to time. So it's a little bit easier to write that. Now, the way we normally work this is we go ahead and get everything on one side of the equation and nothing on the other side. So this is going to be mx double dot plus kx is equal to 0. And that is what we call the simple harmonic oscillator equation, SHOE, simple harmonic oscillator equation. And it's what we call a second order ordinary linear differential equation. But it's not the way we tend to use it. The way we tend to use it is we make the coefficient of the highest order derivative equal to 1. So I'm going to divide both sides by m, and when I do that, I get x double dot plus k over m times x is equal to 0, and this is a second order linear homogeneous homogeneous is the word I wrote there. I barely fit it in there, but I wasn't that sure about spelling it, so I'm okay with that. So second order homogeneous linear ordinary differential equation. And it's called the simple harmonic oscillator equation. So that's the general name for it. And we use that terminology, and people get the impression that scientists are really, really interested in springs. It's not that. It's that basically, if you've had calculus one, in most cases, but in some cases you might have to have had a little bit of calc two, there's something called a Taylor series expansion and something called a Maclaurin series expansion. And in that case, you can expand if the function meets certain requirements. And it turns out that generally speaking, most of the functions we encounter in the physical world for physics do meet those criteria. So we almost always are, or we almost never have to test for it. But if they do meet certain conditions that you'll learn about in your calculus course, then this function can be written as 1 over 0 factorial times the zeroth derivative of f evaluated at x equals 0 times x minus 0 to the 0 power plus 1 over 1 factorial times the first derivative, which is f prime of x evaluated at 0 times x minus 0 to the 1 power plus 1 over 2 factorial f double prime evaluated at 0 times x minus 0 squared plus dot dot dot. Now, we learned, for instance, that a mass on a spring has a potential energy U equals 1/2 k x squared, right? And we also learned that potential energy, when you have a potential energy function, you can treat the zero of potential energy to be anywhere you want. Long as you're consistent, it'll work out. So, for instance, when we were doing a roller coaster problem, I said you can assume y equals zero at the lowest point on the roller coaster, or you might assume y equals zero at the ground near the roller coaster. Both of those are perfectly acceptable. Because potential energy in that case is m times g times y, then you changing from m times g times y being zero at ground level to m times g times y being zero at the roller coaster level, what you've basically done is added an arbitrary constant to the potential energy function. So instead of having just mgy, you have mgy plus some constant. Well, you're allowed to do that. That's the beauty of potential energy is you can add a constant. Well, because of that, if you look at this f of x as being a potential energy function, then you can see that 1 over 0 factorial, by the way, 0 factorial is defined to be 1, but in general, like factorial, 4 factorial is 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. But we went ahead and defined 1 factorial to be 1, 0 factorial to be 1, that sort of thing. So 1 over 0 factorial is 1. F, the 0th derivative, just means the function itself. So the function itself evaluated at x equals 0, that's going to be some constant. And then x raised to the 0 power, that's just going to be 1. So this part right here is just a constant. So if we were thinking about this f of x representing some potential energy function, then that would be some arbitrary constant. Now, if you're actually studying a system like the atoms in a lattice or the atoms in a chunk of metal, what you're studying is the atoms when they're really close to their equilibrium. In other words, you have a potential energy function like that, and you have the particle right here. Now, what can you tell me about the derivative of that function? This parabola looking thing right here. What's the derivative of this function right there? Anybody? This is supposed to be super, super easy. It's not the derivative of
It,
time. Go ahead.
it should be KX now.
Ah, but remember, this is not f equals kx. This is like, let's say, I guess the best way. Well, it would be like y equals x squared. This point down here is what we call a minima. Remember minima, maxima, extremas. So from calculus, what do you know about the derivative of this function, this red function, at that point at the bottom there? Anybody? I probably just worded it so openly that it wasn't easy to answer. How do you go about finding where the minima of a function is? It's one of the first things you learn in calculus once you learn a derivative. Anybody? Okay. So when you're trying to find extrema, that includes minima, maxima, and points of inflection, you take the derivative of the function, you set it equal to 0. So what I'm trying to get you guys to realize is near this point right here, this term is approximately 0. Now, this term right here, that factor is just 1/2 because 2 factorial is 2 times 1, which is just 2. Okay, so we've got a 1/2 there, and then we've got the second order derivative with respect to time in this case, or in this case, it's respect to r to x, so that's okay. But evaluated at 0, so that's some kind of constant. which you might want to choose to call k, for instance, and then it's times x squared. So the whole point of all this is you see that this term right here is 1 half k times x squared. So any function, if you're near an equilibrium point, that function, which we could represent as the potential energy function, would be some constant plus 0 plus 1 half kx squared. Therefore, we see, oh, when we study matter near an equilibrium point, we are studying matter as if it's sitting on a spring. That's a really big deal. So it turns out a lot of different physical problems behave this way. And because of that, we study the simple harmonic oscillator and simple harmonic motion because that's the way things behave near equilibrium. So now that we have that, you have some understanding of what we're going to do. Your author tells you that, hey, this equation right here, the simple harmonic oscillator equation, has a solution. If you were to take this in differential equations, they're going to tell you let x of t equal a times e to the rho t power, and you're going to do some stuff. In physics, we just say, hey, I know it's going to work out to be this, and that's what your answer is going to be. So what I'm going to tell you is x bar double dot plus k over m times x equals 0 implies x of t is equal to a times cosine omega t plus phi. Okay, that's a characteristic solution. And in principle, you could have said it's a sine omega t plus phi. That would be not a problem either. But in this course, we're choosing to use it this way. Now, to understand what that omega is and what the a is and what the phi is, the a and the phi turn out to be stuff that you can only get from the initial conditions. So this is a second order differential equation, and you can think a differential equation is an equation amongst derivatives. The opposite operation of a derivative is the antiderivative, which we know as an integral. So if I tried to undo the differentiation, I'd have to integrate. And since this is a double derivative, in other words, the derivative of x with respect to time and then the derivative of the derivative with respect to time, that's a second order derivative. So that means I'm going to integrate it twice. And remember, if you don't have limits of integration, when you integrate something, you have to add a constant to it. So, for instance, the integral of x squared isn't just what x cubed over 3. It's x cubed over 3 plus an arbitrary constant. So in this case, we have a double derivative. That means we're going to have to integrate it twice. That means we're going to have two constants. Therefore, we're going to have two initial conditions. The initial conditions are usually x of 0 is equal to x0 and v of 0, which is x dot of 0 is equal to v0. Those are normally what it is. They're not required. You just have to have two distinctly different equations about x or x and v or something like that, and then that allows you to determine a and phi. So those two come from that. It turns out that the omega is defined by the differential equation because if you take x of t is equal to a cosine omega t plus phi, and then you say, okay, well, what is x dot of t? Well, that's the derivative of cosine. The derivative of cosine is negative sine, so I get negative a omega sine omega t plus phi, and the omega came out there because of the chain rule. You don't have any choice. You take the derivative of cosine with respect to u, and then you take the derivative of u with respect to t. So the omega just comes out in front. Additionally, x double dot of t is going to be negative a omega squared cosine omega t plus phi. So now if we plug these back into the original equation, which was x double dot plus k over mx is equal to 0, that gives us negative a omega squared cosine omega t plus phi plus k over m times a cosine omega t plus phi. All that's equal to 0. You can see that this equation, since it is Newton's second law of motion, has to be true at all times t. And there's no way that the cosine omega t plus phi is going to make it be 0 at all times t. So we might as well factor that out. And when we do, we get negative omega squared plus k over m times a cosine omega t plus phi is equal to 0, and that means omega is equal to the plus or minus square root of k over m, and we don't deal with angular frequencies that are negative, so we just take the positive sign. So that's what omega is always going to be. No ifs, ands, or buts about it. Okay, you don't have any choice in that. The omega is always going to be whatever is in front of the plane function by itself, because you're going to see later on in this chapter other functions occur. For instance, the same equation applies to a pendulum. If we assume the angle is real small, it applies to a physical pendulum. It applies to a torsion pendulum. All of these different equations are always the same. It's some second order derivative plus some constant times a zeroth derivative is equal to 0. And the constant that's in front of the x is what's going to be taken the square root of, and that's going to decide what omega is. So now we can do example 14.3 really quickly because class is almost over. Example 14.3, it says determine the period and frequency of the car from the previous example. So they want to know t equals question mark, and they want to know f equals question mark. Notice the f is the frequency that we measure in hertz, and the omega is 2 pi f, and f is 1 over t, or you could say t is 1 over f. So that's the relationships that we sort of already know from rotational motion. So in this case, what we want to figure out is omega and the period. So omega is equal to 2 pi f. That means f is equal to omega over 2 pi. And omega is the square root of k over m. So this would be 1 over 2 pi times the square root of k over m. Now 1 over 2 pi stays the same. K was 6.533 times 10 to the fourth, if I remember correctly. Newtons per meter. Let me double check that. 6.53 times 10 to the fourth, yes. And the mass, when it had the 200 kilograms of people in it, the mass of the entire vehicle was 1,400 kilograms. So I can now calculate the frequency to be, I'm going to take the square root of 6.533 times 10 to the fourth, and now I'm going to divide that by 1400. That gives me 6.831, and that is Newton meters per kilogram, so that is actually radians per second over 2 pi. So when I divide that by parentheses 2 times 3.14159 in parentheses, that gives me 1.087 hertz. Cycles per second is hertz, so that's our actual frequency. And then the period t is 1 over the frequency. So t is equal to 1 over the frequency, which would be 1 over 1.087 hertz. And that's just going to be seconds per cycle, but we usually leave the word cycle off. So I'm going to take this 1.087 and raise it to the -1 power. And that gives me 0.91996 seconds. And that's what the period is. Of course, we only had three sig figs, maybe, so that's it. All right, I am going to make another video to finish up this chapter because I've gotten you a good ways here, but there's some more examples we need, and we're going to cover it next time as well. But you guys are free to go. Time's up. I'm going to wait till the last person leaves in case anybody has any questions. Uh, Remember and get your test started, your online test, excuse me, your face-to-face test. You have to get it booked. You can take it as early as tomorrow at the testing center, but you're going to have it completed by, if I remember correctly, I think I set it to Tuesday of next week. But check the announcements where I said that to be sure. Actually, I can check right now, see if I can see it. Yeah, that's this. Let's look in the announcements. But you guys are free to go. Make sure you chat me your first and last name if you haven't done so already. I'm looking in the announcements right now. Yes, final F2F T03 and final exam. The face-to-face test. Uh, so the corresponding practice test will not disappear until April 17th, but rather on April 28th when the face-to-face test is due. So the you can take it as early as tomorrow, which would be the 21st, and no later than the 28th of April. That's your face-to-face test, and then your final exam can be taken anytime, really, pretty much after that. But basically, you have to have it done before noon, by noon on May 4th. So, anybody have any questions?
Do we have class Wednesday and next Monday and next Wednesday?
Yes, in the sense that I'm going to finish up 14 and cover 15 this week and next week. Or excuse me, this today and Wednesday. I might be able to do a little bit of that next week, but I'm definitely signing on at time, and so that's like an office hour for you. But I'm not planning on covering new material.
Okay,
That
thank you
makes
so
sense.
much.
And I'm not gonna, take off for any missed days or anything like that. But I am going to be there in case anybody needs any help.
Were these chapters on the final as well?
Yes, 14
Okay,
and 15 is the last that we're doing.
okay. All right, thank you.
No problem. Anybody else? Jelani, Riley, you have any questions?
Hi, Professor. How you doing?
All right, how you doing, Riley?
Doing all right. So for both face-to-face exams, still
Hmm.
recommendation of like just doing the practice exams and all of that.
Yeah, and like I said, if you find that 14's giving you a problem or 15's giving you a problem, maybe once you've secured your perfect 100 score on one of the practice tests, go back and start doing the individual chapter practice. That way you can drill down on one particular chapter pretty well. But yeah, that's the best thing. And with the new rule that I told you about with your homework, it really doesn't matter too much if you bring your homework up, unless your grade is already helping you and you think another couple points would make it help you even more, then by all means work on your homework. But the real thing is you just need a lot of experience solving physics problems, and the best ones to solve are the ones that I'm going to use for the question bank for the test. So practice test is the best.
I ask out of curiosity, how large is that bank for the final? I'm thinking over 500.
Oh yeah, way more than 500. But the beauty of it is a good fraction of that are all the practice tests you've already been taking. So it's really
Mhm.
not quite as awful, but to be honest with you, it's really more a matter of if you've probably solved on the order of 50 problems from each chapter, you're really in a good spot. But that's sort of the rule is you got to solve at least probably 15 problems from each chapter, but preferably on the order of 50 to 100.
Oh yeah, I've been going crazy with those practice chapters and practice tests, but it's like shoving so much into my head.
Well, if you're learning
and
them,
start
don't
ranking.
worry so much about the volume. If you're looking them up, then you got to really do a lot more volume because it takes so much time for you to learn it if you're not beating your head figuring out yourself. I'm not saying, and in no sense is it cheating to actually look up how to solve the problems, but the more of those that you do and the less of the ones that you figure out on your own, you're sort of robbing yourself a little bit, and it makes it harder to retain the information.
Oh yeah, I feel like the only ones I really have to look up at the moment are still like, was it simple machines, stuff on inclines, like, oh,
Right.
there's so much to put down for that. But yeah.
Yeah. Well, like I said, you can if you run into one that's a problem, especially if it's in one of my practice tests or one of our homeworks, is take a photograph of it and send it to me, and I'll be glad to explain it. Sometimes I'll make a video to explain it. Other times I'll just type up a quick answer or a quick question to ask you to try to compel you to figure it out. But we can also just make a Zoom meeting, and I can meet you somewhere online at some time and help you with it that way.
Okay. One final question for the final exam. Are you doing any proctoring dates or times?
Yes, I put that in that email or that text message, or excuse me, the announcement that I posted. My Zoom
Yeah.
proctoring times. Let me show you this real quick. I'm going to share with my computer screen instead of my iPad. So it says right here, my Zoom proctoring times are Friday, April 24th at 1 p.m., Saturday, 25th of April at 10 a.m., Tuesday, 28th April noon, Tuesday, 28th April 7. These are all times for your face-to-face test. The final exam, I'm leaving up to the testing center, and I also have my times that I'm administering it, which is these times right here.
Shoot. Okay. Oh,
It's a
yeah.
different day of the week, but yeah, it's the same times though. So Wednesday of next week is the final exam in our class, and I have that time that you can come on campus to my particular one of my classrooms and do the final.
Okay. I had plan on taking it honestly closer to the deadline just because more study time.
Yeah, and I'm probably gonna have. I just haven't decided on a proctoring Zoom proctoring time for the final yet, but I will soon. I'll probably do that this week. So you probably can still get me to proctor you. If you do, you have a particular time that might be helpful to you? Because then I'll try to make sure that one works for me.
Not specifically, it was more of just like in case of emergency. Like
Gotcha.
I told you about the situation with
Yeah,
surgery going on.
yeah,
So I'll be in Fredericksburg on the 29th up until like the second or third.
yeah. That's really hard.
And I was
Uh,
like,
don't worry
if
about
things
if
go
you
well,
miss it. Yeah, I can extend it. I'll put in an incomplete briefly and then fix it for you immediately when you come back or immediately once we can get the test done. And sometimes I do it literally the day after I submit grades. So I'll work with you. We'll figure out a way to make sure you can get it taken.
okay. The plan is definitely like to be back early on the third and then
Right.
just study the heck out of that thing. But yeah, if things go bad, that might be a little more difficult.
Yeah,
But
I'm
I'll
sure
of
you'll be
course
awesome.
keep you informed.
Yeah, I hope everything works out all right.
Ooh, I do too.
All right. Have a good one, Riley. Take care.
Thank you. Have a good night.
You too. Jelani, are you still here? And I have no idea if I'm pronouncing your name right. I'm so sorry if I'm not. I don't believe she's here. And I'm just assuming it's a she. I have no idea. I don't think I've talked. All right. Well, that's it. Thanks everybody for coming. Bye bye.